All right, this should be a quick one. So let's take a look at calorimetry next. Calorimetry is, we're going to do some of this in class. Hopefully we'll do some by the end of the week, or definitely for assessment week, but method of measuring the heat, remember, transfer of heat involved in a chemical or physical process. Look, whenever you have a reaction, whether it's chemical or physical, you always have a change in energy. It's just how it works. So being able to measure that energy gives us a lot of information about what's possible, and gives us a lot of chemical information, and that helps immensely. So in order to discuss these transfer of energies and being able to measure them, we need to be able to understand two different things: the system versus the surroundings. So the system and the surroundings is going to help us define the boundaries. And once we know where the boundaries are, we know where to measure. So if I know what the system is and surroundings, we can come up with methods to actually measure these things, and where we're going to start actually doing calorimetry. So the system is a substance or substances undergoing the physical or the chemical process. So the thing that's undergoing the actual reaction that's happening. Sometimes the boundary is pretty undefined. When you run a reaction, let's say in a solution, it's happening within the solution. So like small little pockets within the water, let's say. So the water being all of the other matter present. So the surroundings represent all other matter including the components of the measuring device. So let's say we ran that precipitation reaction. There's an energy change. It does release some energy. Or even when you're taking the solid and we were making those solutions and it turns them hot. So we're adding some sodium hydroxide to water. The system is the space around the sodium hydroxide, or the actual where the reaction is actually occurring. So it's all around within there in releasing heat into the surroundings being the water and the glass and all that other stuff. We only can feel that the water is getting warm because it's making the glass get warm, so on and so forth. So system and surroundings, understanding that the boundary is a little bit flexible. So we have to be aware of the thing that we're actually measuring. There are three different types of systems. An open system is the one that we know the best. An open system, as an example, kind of if we imagine just a beaker, right? There's my beaker, we have some amount of water, and we have just some matter in there. And actually a better example of this would be like a Coke can or a bottle of soda, right? You open it up, and let's say that these little red dots here are the CO2 particles. Well, the CO2 particles will start to come out of solution once it's opened, and they'll start to exit. So you kind of get this exodus of these CO2. And what we have is matter and energy can be transferred and exchanged with the surroundings. So an open beaker, as an example, open beaker or a flask, let's say. Yeah, so that's an example of matter and energy. So it's heating up the air around it, or cooling down, however it happens to be. If it's a cold Coke can, for example, it's transferring the energy to the surroundings, or absorbing, I should say. A closed system, on the other hand, is you can exchange energy but not matter. And the example of this would be something like a sealed flask. So let's say we had a sealed flask. Again, same kind of concept. There's my water, there's my dissolved CO2. Well, here's the CO2, but of course we popped a cap in this thing. That sounded weird, but there we go. It's sealed up. and nothing's getting out. So if I just pull this out of the fridge, the can is cold and it's going to get warmed up by the air and the surroundings in the room, but it is in fact sealed. So this would be something like a sealed flask. And then the last one, an isolated system. An isolated system, neither energy nor matter can be exchanged with the surroundings. And this is a little bit different than anything that we've seen in the past. And this is an example that actually is known as a bomb calorimeter. We're going to see another example of this. And the way a bomb calorimeter works is it has a little chamber and we have a reaction inside of it. And that reaction is surrounded, that little chamber is surrounded by another little bit. And this happens to be surrounded by a bunch of water. So that reaction gets triggered and it releases energy into the surroundings, right? Or absorbs energy from the surroundings. But either way, it's releasing energy into. So we might call this reaction the system, and then the surroundings being the extra water that's present being the surroundings. But most importantly is this entire thing is completely surrounded, across my system there, is completely surrounded by an evacuated container. So we've got just vacuum all the way around it. So an insulated container. And it's going to stop any transfers of heat. So changes in temperature are going to occur. And so the example that we can see here is, here's the hot metal that we added to this water. The heat is being released into the water. The temperature drops for the metal, but as we would expect, the temperature of the water is going to increase, and the temperature of the water does in fact increase. That's an isolated system because it's a direct measure of those two things. In fact, yeah, so let's take a closer look at that. By the way, let's give this a go and we'll talk about it in class on that one as well. But here we have a constant pressure calorimeter. And this is the kind of thing that we would do in class because we don't have the stuff. Constant pressure. By the way, the idea of constant pressure, this is atmospheric pressure. So we're not going to have a pressurized container, right? We're going to have a little cork top to it. You know, gases can escape and can get in. So there's no real loss of pressure. It's always the pressure of the atmosphere that's pushing down on it. So if you can think of a handful of problems with this thing, just in terms of why it doesn't work as well as something like a bomb calorimeter. So a bomb calorimeter is much different. A bomb calorimeter is an isolated system, making it super accurate. Because any energy loss, so we have this little sample, we have the sample down here, and there's the sample that's going to be ignited. You can see it has like this little charge, and these are neat to use. So you can essentially trigger that with a little electrical impulse, and you can light the sample on fire. Generally, you run like loaded up with a bunch of oxygen, so it'll burn a combustion reaction. We have this little stir, so it's going to keep the water flowing, so it'll absorb as much energy as possible, as quickly as possible. And so we ignite this. That's the bomb part of it. It heats up, releasing energy into the surroundings, and ultimately, what you have is the temperature is just going to simply go up, and you're going to measure that. But none of it got around the surroundings because we have this really insulated container, so we can always measure the temperature involved. So let's just briefly talk about the concept of what just happened. In fact, we saw it on the previous page as well. So if I drop that piece of metal in a completely isolated system, and we have water here as well. And I did say that the water was considered the surroundings, and the metal was considered the system. And that's going to help us out a little bit here. So what we do know, what we can say is the heat of the water plus the heat of the metal, it has to equal 0. There has to be no net change in heat. The combination of those two has to be equal and opposite, because any energy lost by the metal is going to get absorbed. Any energy that is lost by the metal that has to get absorbed by the surroundings. Okay, so there's no net change. Another way that we can look at that is I can rearrange it. And instead of saying QW, what I'll say is QW being the surroundings plus Q of the system equals 0. I'm just going to rearrange that. I'm going to put the surroundings on the other side. So the heat of the system is equal to negative heat of the surroundings. And that's the important equation right there. Ultimately, what that means is it's equal and opposite. The heat lost by the system is gained by the surroundings, or the heat released by the system is absorbed by the surroundings, equal and opposite. So that's an important idea. And sometimes you have to actually pull it from the context of the actual sentence. So here we go. So here, give this one a go. And I think that'll do. All right, perfect.